Previous class we have discussed about the deadlock prevention, and now we'll go for deadlock avoidance. Deadlock avoidance says that before allocating the resource to a process, when the process requests it, check whether it will lead to any unsafe state or not. Now we'll say that what is unsafe state? We'll discuss what is a safe state and what is a unsafe state. Unsafe state is a state where there is a chance of deadlock. We are not saying that deadlock will definitely occur. There is a chance of deadlock. So we'll discuss in detail. So if you only go for deadlock prevention, then you have poor utilization of resources and low throughput will be there. And therefore, we may go for deadlock avoidance where some information has to be known before. What are the informations? Whenever a process enters into the system, it must declare that how many resources of which type it needs in maximum. That it has to. And then we have to compute by allocating those resources to a requesting process will lead to a safe state or not. So what a resource allocation state means? What is the number of available resources? How many are allocated? What is the maximum demand? This is called the resource allocation state. That means whenever process will come, it will say that I need 5 hard disks. That is the maximum demand. And out of the 5 disks, how many are allocated? 2 are allocated. So what is its need? Its need is 3. Correct? So now we'll say that what is a safe state. Safe state is when a process requests an available resource, system must decide if immediate allocation leaves the system in safe state or not. So whenever a process is requesting some resource, a check is made whether by allocating that resource, the system will be in safe state or not. A system is in safe state if there exists a sequence P1, P2, P3 up to Pn of all the processes in the system such that each PI, the resources that PI can still request can be satisfied by the currently available resources plus resources held by all PIs. Is not to be confused with these statements. In simple, I'll say, what is safe state? It says that if you suppose I have some processes P1, P2, P3, P4, Pn number of resources processes, and I have some limited resources, maybe 3 or 4 resources. I may have a more number of processes might requiring these number of resources. So it says that we must allocate these resources will be allocated. These are the resources. So these resources will be allocated to these processes. We'll allocate in such a sequence. Suppose I first allocate to P1, then I allocate to P5, then P3, then P4. I allocate in such a way that all the processes can satisfy or all processes can run. It is not that one process will run and holding some resource and requesting for the other and it will never get. That situation will never come. If that sequence exists, then we say it is a safe state. So if I allocate P5, P1, P5, P7, P9, by allocating in this order, I found that deadlock is not occurring. Then it is a safe state. If I found by we do not get any sequence, through which the processes can be, all processes can be satisfied, then we say it is not in what safe state. Correct? So if PI resource needs are not immediately available, PI can wait until PJ has finished. See how simple it is. It says that if PI resource needs are not immediately available, suppose PI is requesting and is not available, then PI has to wait until the PJ has finished. If PJ is finished, Pi can obtain the needed resources, execute, return allocated resources and terminate. Suppose Pj has finished. When Pj will finish, it will return whatever it has held before to Pi, so that Pi can start its execution, it will over and return all the resources, so that another process Pi plus 1 can execute. Is it understood? So whenever a process will take, so that all processes in the system must be satisfied. All processes in the system should be satisfied. Let us take an example over here. Suppose this is an example. A system has 12 magnetic tapes. Assume that we have 12 disks are there, 12 drives are there. 12 magnetic tape drives are there and 3 processes are running. Try to understand the concept. In your system, only 3 processes are running, 12 magnetic tapes are there. That means all 10 it will return over here. A process can only return whenever all it needs is being availed and it has finished its execution. Similarly, look into the process P1. What is the maximum need for P1? 4. And currently how many are, current need is 3. Current need is 2. Correct? Current need is 2, maximum need is 4. That means if I give 2 tape drives to process P1, it will definitely finish because it requires only 2 more. 2 are allocated. If I give 2 to this P1, then the P1 can finish its execution because its need is current need is 2. 2 has already been allocated. If I give these 2, this will finish and it will return this 4. Similarly, P2 current need is 2. It requires 9. It requires 9. The current need is 2. So that means if I give 2, it will return all those 9 to me. Right? Is it understood? Is the problem understood up to this? Or any doubt? Is it understood?
Sir.
Okay.
Yes, sir.
Okay, now see here. So suppose this is given. This is a scenario given. 3 processes, some maximum need and current need. If the system allocates the rest resources to P2, look here. If the system allocates rest resources to P2, can you tell me how many rest resources have? What do you mean by this rest resources? How many rest resources are there? Who can say? How many rest resources are there? Okay. 3. Yes. How it is 3? Just see over here. How many we have? This is the current need. The current need is how much? Current need is 5, 2 and 2. This is the current need. We have total 5 magnetic tapes are there. We have total 12 magnetic tapes are there. We have total 12 magnetic tapes. So rest of the resource, if we allocate, if say that if the system allocates the rest of the resources to P2, so what will happen? If you allocate to P2, so can the P2 will finish? If I allocate, suppose this 3 will allocate to P2, it will have 5. This will have 5, and this 5 will not satisfy the P2 requirement, so P2 cannot finish. As P2 cannot finish, this will not release. This will not release any resource. So not only P2, P1, P0 will be kept waiting like that only. Correct? But just think of, if I allocate to P1, what will happen? If I allocate to P1, the 2 I will allocate, So it will return all those 4. So now I will have 5 resource. That 5 I can give to P0, so that P0 will over, and it will return all those 10 which can be given to P2. Are you getting me what I'm saying? If I give to P2, what will happen? If I give to P2, so this will be 5, but this cannot finish because maximum need is 5. So that means if I allocate in that order by allocating P2, this will lead to an unsafe state. But if I allocate to P1, the P1 will definitely finish. So once it will finish, whatever it has held, it will return back. This 4, it will return back. I may give it to P0. P0 will return back this 10. So then I can give to P2 and I can satisfy all these 3. So from this I can see P1, P0, P2. If I allocate in this order, it is a safe sequence. But in the first case, if I allocate to P2, it may lead to a unsafe state. Correct? So what you understood over here, unsafe means deadlock. Is the unsafe means deadlock? Is the unsafe is equal to deadlock? Anyone? Is the unsafe ensures that the system is in deadlock?
Yes, sir.
So look here. It says that if it is in unsafe, it may be in deadlock. We will not say that it is in deadlock. That means a unsafe state may lead to deadlock. In other words, means other way I will say, if it is in safe state, deadlock will not occur. Try to understand. In safe state, deadlock will not occur. So that means if you are in safe state, definitely deadlock will not occur. If you are in unsafe state, deadlock may occur. If you are in unsafe state, deadlock may occur. All deadlock states are unsafe. All deadlock states are unsafe because, so if I, out of the total, one part is safe, another part is unsafe. So in the safe part, if I put something, definitely deadlock will not occur. Out of the unsafe, some part are deadlock. So we are not saying that all unsafe are deadlock. Goat has a head doesn't mean that those having heads are goats, right? So it's not like that. So if you wear mask and sanitize and every rules you will follow, the deadlock will not be, or corona will not affect you. But if you do not wear sometimes, doesn't mean that definitely the corona will attack. It's not like that. So safe state is where deadlock will not occur. Unsafe says that there might be a chance, the deadlock chance is there. Right? So, but if a deadlock occurs, do remember, ensure that definitely it is an unsafe state. So we can have some conclusions over here. What are the conclusions over here? You can see there are 2 states. One is safe state, another is unsafe state. If I allocate some processes to resources over here and it is in safe state, that means deadlock will never occur. We ensure that deadlock will never occur. So we'll try to put over here. If my process, by allocating those processes, it will be in unsafe state. If it is in unsafe state, I am not claiming that it is in deadlock, but I am claiming that there is a chance that deadlock may occur because all deadlock are unsafe. All deadlock are unsafe, but all unsafe are not deadlock. Correct? I hope it is understood. Is it understood? Anyone having doubt?
Yes, sir.
Okay. So now it says a system A system is in safe state. If a system is in safe state, no deadlock. If a system is unsafe state, there is a possibility, chance of deadlock. Correct? So if it is a deadlock, then it must be in unsafe state. So avoidance means ensure that a system will never enter an unsafe state. So deadlock avoidance means we'll try not to put the processes in this area, in this unsafe area. Correct? So for that, we use two algorithms over here. We use two algorithms, single instance of a resource type, and to use single instance of a resource type, we use the resource allocation graph, and the second one for multiple instance resource type, we use Banker's algorithm.
Sir. Starvation will come under unsafe state.
Hello, can you repeat? I could not hear properly.
Starvation will come under unsafe state.
Starvation is not under, actually, very good question. So actually starvation is not unsafe. Actually starvation is not considered over here. Starvation is a situation we are not saying that starvation we cannot come back. So we have a hope that we will come back from there. So it is not that it will be an indefinite blocking kind of thing that you do in a deadlock. But even if the process is as in the safe state, it may be in the starvation. So I know that the resources can be granted. Suppose a sequence is there. It is in safe state, I have allowed, but they are getting resources after a very long time. So even if in the safe state, it may be in a starvation. So we are not saying that starvation will only be in the unsafe state, right?
Yes,
Okay. So what I say, so deadlock avoidance algorithm are two types. One is for a single instance resource type. That means every resource has only single instance. I have one hard disk, one pen drive, one monitor, one memory. So every instance has every different resource type has only one instance. In that case, we'll use a resource allocation graph. If you have multiple instances of resource type, I have 5 hard disks, 12 pen drives, 6 tape drives, 4 memory. So if you have multiple instances of multiple instance of resource type, then we go for Banker's algorithm. So Banker's algorithm is very, very important. It definitely usually comes in the exam. And this is as well, but we'll now go for this resource allocation graph, and then we'll go for this Banker's algorithm. The resource allocation graph. Look over here, very simple. All those I will say, there are many texts are written over here. Very simple, I will say that you must have understood the resource allocation graph that I have, RAG graph we have already discussed. We have already discussed earlier RAG graph. This is the RAG graph we have, resource allocation graph. The processes and resources are vertices. There is two edge, request edge and assignment edge. And if it contains a cycle, if it doesn't contain a cycle, there is no deadlock. If it contains a cycle, there might be a deadlock, right? So not all cycles are deadlock, but if it is a single instance, it is a deadlock. That we have read. Simply the same thing we are saying over here. If it is a single instance resource type, before suppose I have these are the, remove this dotted line. Dotted lines are not there. I have two processes. There is two resources. R1 is given to P1, R1 is assigned to P1, P2 is requesting to R2. Now, for example, P1 and P2 are requesting for R2, right? Now, we'll check that whether by allocating this, is it forming a cycle? So what we'll do, we'll make a edge, dotted edge, which says a claim edge. That means it is claiming. So if it is claiming, so we'll put a claim edge and check whether it forms a cycle or not. If it forms a cycle, we are not saying it is a deadlock, but it may be in a unsafe state, but it is a non-safe state. And we know that if it is a non-safe, deadlock may occur. So therefore, we check in the resource allocation graph by putting a claim edge before allocation. If it forms a cycle, so we'll say that resource cannot be granted. So that is being explained over here. The RAG is a new type of edge known as, here we will take what? Claim edge. What is claim edge? Suppose there is a edge from process to resource. Claim edge is always from process to resource. PI to RJ indicates that PJ may request resource RJ. This is PI actually. The PI may request resource RJ sometime in future, which, so this is, it may request for the PI may request resource RJ sometime in future. So if there is a edge from PI to RJ, that means PI may request for RJ. So what is claim edge is doing? Claim edge converts to request edge when a process requests a resource. So that claim edge is converted to request edge whenever a process requests a resource. So request edge converted to an assignment edge when the resource is allocated. Try to understand these two. It says that claim is converted to request when a process, process request a resource. Do we have class after this? Hello?
Yes, sir.
Oh, then I have to take the attendance because it will end.